We'll look at another example using Bayes' theorem today with continuous data. And it maybe illustrates a little something about normal distribution and a quadratic form. We'll do a Bayes example and then talk about some material that would be on the final. I have not posted any study material yet, but during the last week of class and study material we posted and we do some review and go over some things. But the main work to do to finish off the course is working on your projects and presentations. And this homework had to do something with the beta binomial Bayes example. And so that's kind of the homework example that would, to illustrate the method. We would, include something about that on the final. The only thing to put it on, on a homework would be another Bayes example or something to kind of pull things together, but we'll do that more in review. So, yeah, thinking about the projects and presentations. And so, there's the next week when you can take the break. We aren't meeting on Monday. You do have that extra day and the weekend to get a project together. The report for the presentation, the plan is to have them due on the December 6th. To fit everybody in terms of presentations, it would be desirable to have some on December 4th. Now, I think the class that's in here after us is a Monday, Wednesday class. So that Friday we could go over and have more that day. But if anybody, it would be great to have a few volunteers. You'll do that, right? So do Wednesday, so maybe I can, I'll just write it down here. So Emily.
Emily and I were, yeah.
Oh, okay. And Abby, right? And I know your name. Liam, right. Liam Gavin, yeah, right. So that would be a couple. And for a two presentation, it could be a little bit longer. You need both materials. And so out of the class, if we get a couple more for that first Wednesday, it will make it a little bit easier on that Friday, right? If we don't use the full time on that Wednesday, there'll be more time for questions and things like that. But everybody, it'd be nice to have 10 minutes. So that's why putting it all on the last day would stretch it a little bit longer. So, the final will be scheduled according to the registrar. For this one, we'll allow a sheet of notes. Both sides. For that calculator, we're doing some computations, and we'll talk about the form of the final. How would we ask about some of these things that involve simulation or computation and things like that? There's elements of it that can be done with computationally, and then there's some parts that are interpretation, and so kind of we can address things like that. So Bayes example, right? So the first couple ones we did had discrete outcomes, right? Binomial number of successes or Poisson number of counts, but we can do this with continuous variables too. So let's say that x given a mean and standard deviation might follow a normal distribution with some mean and variance there. And for the time being, we'll use, and we'd observe x1, x2 up to xn. Say they're independent, identically distributed. They all come from that same distribution. The probability density function for one x variable, one observation, is the normal density curve. So it's 1 over 2 pi sigma squared and the square root of all that. And there's indeed negative 1 over 2 sigma squared, x minus mu quantity squared. So that's the density. This is the density, the equation that gives us this bell-shaped curve centered at some value of mu. If we have n independent observations, then our likelihood is the product of this for all n observations. So our f of x, meaning the little tilde means all of them together, x1 through xn. If they're independent, it's a product, f of xi given mu sigma squared. And there's this 2 pi sigma squared for each of them. And it occurs n times. And I kind of like to put the square root as a 1/2 up there. Right? So this 2 pi sigma squared to the 1/2, meaning square root, then it's kind of nice to put it like that, I think. And then you'd have this thing multiplied together n times. And it's all in the exponent, so it becomes a plus in the exponent. You can pull out the 1/2 sigma squared, and there's a sum here of xi minus mu squared. That's a little bit, gotta make a little separation here from the picture. And the thing that's in here, let me try to draw that a little bit neater, right, is 1/2 sigma squared is here. So this has 2 parameters. We could be interested in mu. We could be interested in the variance. We could be interested in both of them together. We might be interested in a ratio. Like the standard deviation of mean is something called coefficient of variation. And so even if, say, different species of animals or mammals have different sizes, different means, and different variances, in some biological problems that ratio, that coefficient of variance, like average versus standard deviation, can be more constant. And so that might be kind of interest. So there could be many things of interest here. And so in principle, you could have these 2 unknowns. We're just going to work through the case where sigma's known. Like, pretend sigma is known. Right? For example, if we thought sigma was 5, right? It simplifies things. And then we only have one unknown parameter. Right? So then we can ask the problem, what is mu? We've approached this with unbiased estimation or maximum likelihood estimation, kind of ad hoc things. You think mu is small, maybe you shrink it towards 0 a little bit, right? But in a Bayesian context, we put a prior distribution on mu. Right? Where do we think it is before we would ever see any data? So the Bayesian approach of prior distribution on mu. Right? And so we're going to do some type of f of mu distribution. We're going to put some curve on that, and it's a mean. Maybe you have some idea where it is. If you're doing test scores, you may have some idea where you think the average is. If it's health measurements, you have some idea where the average would be. And so one possibility is to say that mu a priori is normally distributed around some average with some variance. So this would be the prior mean, or kind of prior guess of where this is, and this thing would be a prior variance that would kind of encapsulate how sure we are of where we think mu is. Right? If we don't have much of an idea or don't want to put too much effort or input into it, and rather say, well, it's kind of vague, we will probably make that a big number. Right? But if you have a lot of prior studies, a lot of information, you might be willing to make it pretty tight. People might debate how strong that should be and how much this should be, and the more opinionated you are, the more subjective information you want to put in there, you might make it tighter, but then some people might object, say, oh no, you're influencing things. But that's part of it. You make some choice. So that's the prior. So the density here is also a normal curve, right? 2 pi now sigma 0 squared, e to the negative 1/2 sigma 0 squared, and there's mu minus mu sub 0. Mu sub 0 plays the role that mu used to have, and mu is the thing that we don't know. It's given the distribution, so it looks like it's in the place where we used to have x. Right, so that's our prior density. Right? Now, we observe our data, what's the posterior distribution of mu given our data? How do we update that to reflect our information? Right? So this is where we get to do some completing the square and rearranging of terms, kind of more the algebra application of things. Right? So what we want to do is we have our data, right, mu, and this is equivalent to the density, the prior times the likelihood over the marginal distribution of x's. It follows the same general form of going from prior to posterior and so on. This thing, f of mu, f of x1, x2, f of xn, given mu, the denominator, right, is the marginal distribution of this. But if you have a joint distribution of mu with the x's, you get rid of it as mu times the conditional distribution here. If you integrate out mu, like actually take the integral to get rid of mu, that gives the marginal distribution. So the denominator can be written as the exact same thing as the numerator with mu, and we integrate out mu. We actually do the integration. Right? And mu goes from negative infinity to positive infinity because it has a priori normal distribution. And that goes over the whole real line. There's not much probability way out there in the tail. And it really gets small, but that would be it. And because of this relationship, things that don't involve mu, you just have x's or something that's kind of separately, or a number like square root of 2 or square root of pi, it's going to basically cancel because it could be pulled out of here and out of there. So sometimes Bayesians talk about the posterior distribution is really proportional to the prior times the likelihood, or at least the proportions of that involve the parameter. And that other stuff it's important, it's a normalizing constant. It makes it integrate to 1. So technically you need to keep track of that stuff. But to make things a little bit easier, we can just focus on the key part that involves mu and see what that looks like. Right? So we're going to make use of this proportionality, that little alpha-looking thing, proportional to. Right? So that this was the density, what was up there was the density of mu given all the x's. It's proportional to the prior times the likelihood. All the x's given mu. Right, so we're going to multiply these two functions together and then rearrange things to see what, kind of solving it for mu. Not really solving it, but rearranging it, focusing on mu. Right? So what are we going to put in there? Well, this is the normal density for mu, and that was that likelihood piece. I'm going to kind of drop out these extra things with where sigma is kind of a separate multiplier. Right? And so we're going to write part of that there. So the f of mu given the x's is proportional to, there's that e to the negative 1 over 2 sigma 0 squared, mu minus mu sub 0 squared. And then the likelihood, there's also a multiplier out here, but it would just cancel. And then there's the likelihood here, there's a multiplier with that 2 pi and sigma thing, but that would just cancel because we're treating sigma squared as known. And so we need this part. It has the sum of xi minus mu squared. Right? Right, and that's kind of keeping those key parts. So there's mu there and mu there as a function. Right. And what we're going to do is combine those things in the exponents and try to write it as something like mu minus some stuff squared, right? This is kind of just stuff right there. So we're going to try to make it into a quadratic form, so it's mu minus that. Why am I doing that? Well, if I do that, most normal terms, distributions have this kind of mu minus a mean, right? This is going to be the posterior mean. So I'm going to put those together. In the numerator, up there top, right, I'm going to make, before multiplying those together, I'm going to look at this little thing here. The sum of xi minus mu squared. Right? There's a way to simplify this a little bit. Right? Do a little numerical trick. I'm going to add and subtract x bar inside, and then square it. So I'm going to take xi minus x bar here, then I'm going to add x bar minus, just put that in there and square it. When I square this part of it, I get xi minus x bar squared. Right? I'm going to take this part and square that, x bar minus mu squared. And then there is a cross product, right, with this square up here. This part, this is like a squared, b squared, and then we get 2 times ab. So it's the sum of xi minus x bar minus mu goes there. And if you think about it a little bit, oh, here's this xi minus x bar squared. This x bar minus mu is the same for all n. It's just there's not a subscript I in there. Right? So it's n times x bar minus mu squared there. And this part here is actually 0. This thing can come out, and the sum of the xi minus x bar is actually 0. It's a little algebra thing. So this thing reduces to this, right? And we can concentrate on this part that involves mu. That is, there would be this part that is xi minus x bar squared in the numerator or the denominator, and so one more thing could cancel. One more simplification can happen. So writing out all the details very explicitly takes up a few pages, so I'm kind of jumping a little bit, trying to get to the summary. Right? So what we're going to have up in the exponents, once I drop out just a little bit more, in the 1/2, the negative 1/2, I'm going to ignore that. The things that we would have adding up together over there, I would focus on this thing squared, plus the 1 over sigma squared, and there's an n x bar minus mu squared. So kind of pulling out just the things out of the numerator. So working with the algebra of all this in normals, is a little bit to get used to. We're just kind of illustrating it. The book has a few more details in there. But let's simplify. Let's expand these things and put it over a common denominator and see what we get. So if we put it over 1 over sigma 0 squared, sigma squared, we would get a sigma squared, and then there's a, is that how it works best? Yep. Multiply that out. This thing, sigma squared minus 2 mu sub 0 plus sigma 0 squared. And then this one is an n sigma 0 squared. And there's an x bar squared minus 2 mu x bar plus mu squared. Right? So we're interested in mu. So we'll pull the parts that have the highest power of mu out front, group those together. We'll group the ones that have mu in there singly together. We're going to get a quadratic expression. Right? And so here's this 1 over sigma 0 squared, sigma squared, and then so we're going to get a sigma squared plus n sigma 0 squared times mu squared. That's this one, right, and this one. And then there's a minus 2 mu. What's the multiplier on that one? Well, there's a sigma squared mu sub 0 there. This one has n x bar sigma 0 squared. Plus, another term that would not involve mu. There's no mu over here in that. Right. you can keep track of all the details if you want to make it work out. I'm going to pull this out and just have mu squared minus something, like you would have for a quadratic equation. Right? So this is algebra day. Oops. Well, not abstract algebra day, right? But just mechanical algebra or something like that. So this was a sigma 0 squared. So I'm going to pull out that thing up here, sigma squared plus n sigma 0 squared over sigma 0 squared, sigma squared. There, that leaves a mu squared. Over here, we have the same thing in the numerator. But because we've pulled this thing out, right, it would just multiply here, it'd be the equivalent there. But it wasn't over here, so to make things balance, we need this sigma squared plus n sigma 0 squared here. And there'd be all this other stuff over here where I'm not going to exactly worry about the details. So now you have mu squared minus 2 mu times something, right? And completing the square, you can do by taking this and adding its square in here, and then subtracting its square as well. And there's a lot of details I'm not writing there in terms of all that. If you want to take a couple more pages, you can write it out, right? But it's called completing the square because once you add in the right thing here, you can write mu minus this thing quantity squared. Right? It's not a bad thing to work on, right? To think about. So kind of in the, if you had mu squared minus 2 mu times a, and you added a squared and subtracted a squared, right? This would be mu minus a quantity squared plus this extra stuff, right? Mu squared minus 2 mu a plus a squared. So completing the square is, can be done by kind of adding and subtracting the right things. So you do get a square, a quadratic. More generally, it's a quadratic form, which is very important to normals and measurements in space, right? So that's what we will do over here. Add and subtract this, and then make it a square. And that extra stuff over there is not going to involve mu, because it's going to be this stuff over here. So again, I'm claiming that all cancels. So what we end up with, once we complete the square, the thing out front, sigma 0 squared, n plus sigma squared over sigma 0 squared, sigma squared there. And then we get mu minus sigma 0 n x bar plus sigma squared mu sub 0. And this is over sigma 0 squared n plus sigma squared. Right, that thing squared. It was going to negative 1/2 preceding all of that stuff. Right? Where was this expression? This was up in the exponent. Right? So it was really kind of e up to that exponent. So after all this, it looks like, believe it or not, that we have another normal density. Because we have mu minus something squared, and then e to the negative 1/2, and this is like 1 over the variance. That's there. Right? So it turns out that if the prior on mu is normal, and the data model, the likelihood is for normal, the posterior distribution is again normal. Right? Very nice when these conjugate distributions are used. You don't have to. You can do other things and do computation in other ways. Grid search, resampling, there's a lot of interesting things that go into that. So kind of the next level of books that would do more with computing involve more simulation of probability distributions. So this ends up being that the answer of mu given our data x, the posterior distribution, ends up being normal. And the mean, the thing that is subtract it over here. Here's the posterior mean. Sigma 0 n plus x bar. Right, x bar here. X bar plus sigma squared mu sub 0 over sigma squared n plus sigma squared. And then the thing that's up on the front of it is like 1 over the variance, right? Because we always had 1 over sigma squared there. So you take 1 over that, you get sigma 0 squared over sigma 0 squared n plus sigma squared. Right, and so that's the answer. We can do a little bit more with interpretation to see what's going on with this posterior variance. There's a nice way that could be written. So variance is big when things are imprecise. Right? So there's another expression that called precision, which is 1 over the variance. Precision is 1 over variance. So if variance is small, precision is high. If variance is big, precision is low. If you write 1 over this, right, it's, well, this thing is like 1 over the sum of 2 precisions. There's a prior precision, 1 over sigma 0 squared. And the accuracy from the data, right, the variance of 1 would be sigma squared. So its precision of 1 would be 1 over sigma squared. But if you take an average of n, it's like sigma squared over n. So 1 over that is n over sigma squared. So the variance here is 1 over the sum of the precisions. It's kind of a different way of looking at accuracy. Right? So if you put these over a common denominator, the common denominator here is going to be sigma squared 0 times sigma squared, but that's taken up to because it's 1 over 1 over, right? And it goes up here. And the thing that would be over here, you get a sigma squared over here, and then you get n times sigma 0 here, and that's that thing, right? So it turns out that as you're adding more observations, as n gets bigger, this is the precision in the denominator. You add observations, your precision goes up, and your variance goes down. Right, so that's a variance relationship that comes out of that. These type of interpretations, like is it an average or something like that, or these interpretations are kind of specific to the normal model, or the other ones. It works out sometimes for these, and people have figured out ways of looking at it. But what does that complicated thing kind of look like? Right? This thing is actually a precision-weighted average of 2 things. It's an average of x bar and mu sub 0. Right? And it's weighted by these precisions, which is kind of, I think it's kind of neat. So the precision of x bar is n over sigma squared. Right? And the precision a priori of mu sub 0, we gave it a precision, a variance of sigma 0 squared. Right? And so if you take a weighted average of those things, with the weights being like the precisions, you get that. And honestly, I don't know how long it would take you to figure out an interpretation like that, but I've seen it in books and things like that. So you're going to put these over a common denominator, so you can get sigma squared times sigma squared 0. So it's like putting the sigma squared times sigma squared 0 up here. Right? So if you multiply here, that's why that's canceled, and that's where you get this one. Sigma 0 times sigma 0 squared times this one, the sigma 0 squared, and you get the sigma squared, and so on. So anyway, that's kind of interesting that it kind of naturally combines them in a way you can kind of think about. Right? As the sample size gets big, variance gets very, very small. If you divide by kind of 1 over n here, in both sides here, you can see that as the sample size gets big, the thing that matters is x bar. Right? It's going to get much more weight for bigger sample sizes. And eventually, the controversial pick of that prior is going to go away. Right? So anyway, that's what you get for an estimate. We'll look at a data example to finish up on this, and then I'll just mention 2 things. some people do something called empirical Bayes. So how do you choose the prior? Well, the expectation of x, of our data, there's a nice result from probability theory that says the expectation of the x is the expectation of the conditional expectation. And the expectation of x given mu is just mu. But a priori, under our prior distribution, it was mu sub 0. And so a method of moments type of argument would say, how do you estimate mu sub 0? Well, use x bar. So we kind of use method of moments to kind of justify using the data to set up some of the prior. Does a little double use of the data. People that do empirical Bayes try to account for that in analysis. So there's a little bit more trick to it. But sometimes people try to use the marginal data or some data source to try to guide that rather than come up with that out of the blue. Part of that is it's supposed to be less controversial than just picking it. Right? Another thing that people do is pick a prior, de-emphasize the prior choice, but still use some of the Bayesian mechanism to come up with the posterior distributions and to report distributions. Right? So, for instance, in this, the prior mu was normal at this at sigma 0 squared. Well, so this is some curve, right, centered here at mu sub 0, and the width here, this point up here might be about mu sub 0 plus 2 times its standard deviation, and mu sub 0 minus 2 times its standard deviation. So one way to kind of de-emphasize that and say, well, we don't really know, we're not going to try to influence, we'll let the data dominate, would be to give the prior less precision. Right? Make the prior more variable so that the data precision is what dominates quicker. So less precise prior that we might use. Let's choose a big one. And in fact, you can, in some cases, let some of these parameters, which normally wouldn't be infinite, for real probability distribution, but you can let them be effectively infinite or take a limit, and still, if you have enough data, you see a couple observations, you can still get what's called a proper posterior distribution. Even if the prior is flat, you can't have something that has infinite variance that integrates to 1, so it's not really a probability distribution, but you multiply things together, certain things cancel, and you still end up with something that's a real probability distribution. So this would say, basically don't let that go. If you do these cases, this thing, whatever this ends up being, as the precision here goes to 0, you end up centered at x bar with a variance that's like sigma squared over n. And it looks like basically what you would do for a confidence interval. So there's ways to kind of manipulate those things or make connections so you avoid a little bit of the so-called subjective criticism. So there's a few technical things that are kind of interesting to innovate and make this work for inference. Right? So let's look at a little example. So birth weights of, for new mothers, of birth weights of their children at term. What do you think is the average birth weight in pounds? Yes?
6.
6 pounds? 6 pounds, right? And how strongly do you feel about that? What would surprise you?
Like on a scale of 1 to 10.
Yeah. Well, you know, you could do different assessments like that, right? So people like Kahneman and Tversky and others, you know, people try to really do those assessments to get those things. But what would be surprising? Could it be 5.5? Could it be 7.5? 8? You know, what is, you know, seems like a reasonable range. So we're going to collect some data, or I'm going to tell you some data summaries, right? And we're going to see, you know, how things change, right? So we don't want to influence it too much, but if the guess is pretty, you know, reasonable, you know, you don't want to allow 3 pounds to be the average. You don't want 12 pounds to be an average. That just doesn't make any sense. I don't think anybody would object to ruling that out, right? So what do you think? Like somewhere between 6 to 8 pounds? Like plus or minus a pound. You know, somewhere the average, maybe somewhere in there, right? Well, if we do that, that kind of implies about sigma of about 0.5, plus or minus 2 standard deviations. You know, maybe you make that 3 standard deviations and make that a little bit smaller. Let's say we do it 0.5. Maybe I'll do it, you know, 0.6. Let's use this. Let's use this. Let's use this number. Right? So then we get a sample of 80. And these happen to be mothers of European heritage. When I looked online at different places, there was distinctions between European heritage, you know, South Asia and China in terms of average birth weights. And some sites made more distinction between different race ethnic categories. Surely there's many things that depends on. But let's say we got 80 new births, singleton births, and the average was 7.7 pounds. And 6, right. So there's kind of 2 things here. Well, let's say, you know, our prior was kind of plus 1.5, like sigma 0 is what that has to be, right? So there's really 2 variances. There's kind of the prior variance, and then there's the variance of the data. And the variance I can infer from different sites is about 0.6, 0.6. So the data is actually a little bit more, well, see, this is variability for one measurement. Right. And this is the prior variance on the mean. They're little different things. Or prior standard deviation for the mean. So they're really kind of different things. Right? It's not saying that one measurement is 0.5. We're not really kind of debating whether it's 0.5 or 0.6. Because one's a prior variance, and the other one's a measurement issue. Right? So Bayes then would say, given our data, right, and what we really need is that under this scenario, it's just the average. If you have the 2 parameters, you would need the sample variance, and the book shows that one. But this is going to be normally distributed. 7.7, and this is 80 n over, you know, 0.6 squared for that accuracy. And our prior was 6, and it's like 1 observation and 0.5 squared. And then this one is 80 over 0.6 squared plus 1 over 0.5 squared. And the variance is like 1 over the 2 precisions, so 80 over 0.6 squared plus 1 over 0.5 squared, like that. I'll have to compute that one. So the mean, 7.7 times 80 over 0.6 squared plus 6.0 times the 1 over 0.5 squared. And then the denominator is the ratio, some of these weights, So that comes out to 7.67 as a posterior mean. That number ends up being, right, 7.67 pounds. Right? So you kind of pulled it down from the 7.7 average toward the 6.5. Right? And maybe that's very reasonable. If your prior opinion was had some validity to it, and maybe this sample just is a little on the high side, that could be doing some very good things, right? If you got 800 and it was 7.7, it's going to be quite close to 7.7. And that initial prior guess won't. Right? What precision do we get? Well, so if we just had a sample, right? If we just looked at x bar in our usual way, and we took like sigma over the square root of n, that's going to be the 0.6 over the square root of 80, and we think about that as a standard error. So 0.6 over the square root of 80 is about 0.067 pounds. But in Bayes, we're going to take the variance, so it's 1 over the sum of the two precisions over 0.5 squared. And the square root is to get it back in the standard deviation scale. 1.66. Very close. Right? It's really driven by that likelihood and accuracy of the measurement. So they're very close. A little bit different calculation. Right? And so this thing is 0.066. That's squared. Right? So this one is 0.067. This one, I guess, is smaller because we have one more observation kind of incorporated in that prior, and that one observation has a little less variability, so altogether it's like having a little more information. So it's a little more precise. But if you needed to do a probability statement for percentiles or anything like that, you could just use that. And if you had a different prior distribution, it could be slightly different. If you use empirical Bayes or the limiting one, you can debate the merits of those different things, right? But any questions? So one thing that I've been influenced by, is my advisor. We talked about, we want confidence intervals so that over repeated behavior, 95% they should cover. But now we're doing this Bayes thing, right? So should Bayes also be compared that way? And the answer for some people is that, you should look at Bayes over time and see that Bayes is producing good estimates, right? And so it has some of the articles that have had an influence is, Bayesianly justifiable and relevant frequency calculations for the applied statistician. So, Bayesianly justifiable means using Bayesian logic to come up with posterior distributions and make probability statements. But the relevant frequency calculations are things like, how does this perform over time? If I'm choosing ridiculous priors and ridiculous models, it's not going to work well. All right, so you still have to check, does the data look normal if you're using a normal model? Is independence realistic and things like that? And is it frequency calibrated over the long run? Right? If there's slight deviations from the model, if things break down, it's kind of not very good. And so there's ways that these different applications are merged from these perspectives. And I kind of use the Bayes as a way to generate inferences in bigger, harder problems. Dealing back to likelihood with multiple levels and complicated missing data structures. Data coming from different sources, I think, can be quite difficult. But you can think about probability models that can encompass different types of measurements, or measurement given that, conditional distributions, and things you can really think about in a scientific context, and then putting it together in a probability model. What's the price you pay? You might need to put prior distributions on some parameters and do more with calculations and computing, but in the end you can get some probability statements. So anyway, I might put those up there because I think they're kind of advanced and have some technical things that are subtle, but it talks about what we've been talking about in class and tries to bridge that gap. Right. But anyway, that's what we're kind of going to do in terms of the Bayes things. On Monday when we come back, really is a day to talk about summary and review and things like that, and coordinate a little bit more the presentations and so on. So I'll say some stuff now that's on the final. I mean, part of this is some students couldn't be here or aren't here. A couple called in sick, and a couple are away for things. But so it provides an outline. Although it's a couple weeks away, studying for the final is, at some point you're going to want to start doing that. The projects, of course, are more presentations, probably more pressing. But these are some things that can be on the final. I won't be completely comprehensive in terms of every detail, but we'll try to hit the highlights like we've done on a number of things. And so for representing the Bayes, the kind of binomial beta calculations. This was done on the homework 10. It's a section 11.3 that's there. So things like finding alpha and beta for a mean and variance. So you have a certain prior mean, prior variance that you want to match, and you can determine alpha and beta for a certain beta that matches that. Right. Update parameters through the appropriate formulas. By this, I don't mean doing the probability, like the integrals and things like that, right, that are kind of behind it, but using the end result, right? You get so many successes and failures where you add something onto alpha, you add something onto beta, and you get a new mean, right? So using that part of the formulas for it. Interpretations. Interpretation of a Bayesian interval. Instead of being a confidence interval, it is a probability statement. You can take it directly as that, right? So it's a little bit different. I might show you some graphs. Of things or simulation output to do things like which one would be the corresponding prior, here's a prior graph, and now you have some data, what was the posterior, how should that change? So kind of figuring out some of those correspondence things. I mean, mostly for Bayes. Chapter 10 has things, categorical data. So there's a different chi-square tests, either the x squared or the g squared tests. There's a permutation test that was used. For testing whether two dimensions are independent. For these, given a margin, we'd find the margins, find the row totals, column totals, calculate an expected value. State hypotheses. There's a Fisher exact test. So we did a little bit with that, mostly through the command, but there's a little bit of rationale in explaining how you would compute that. We didn't do a lot with actually computing the hypergeometric probabilities, but we can think about why is one table more extreme than the next one. If you calculate expected values, the more extreme tables are further away from expected. Right? So if you change one of these with fixed margins, then the other ones have to change in a certain way. So something like that. And then some interpretation. Of the test result. Right? You have treatment and control, and you have a certain percentage success under those two, and if they're different, and then you show with one of these that it's statistically significantly different, right? Then that's kind of proving something. But if it ends up you get a p-value of 0.2, 0.3, something, it's not significant, even though there's difference in the rates from the sample, it doesn't really prove that you haven't convinced anybody that it's actually different. So there's kind of that. We've done some things with Chapter 8 hypothesis test. So some amount of that, I'll look back at exam 2 and what exactly we did there, because we didn't do all the formulas, right? But some hypothesis test with a formula, right? And then there was some bootstrap T procedure. We were focused on, why would you do this? Why would you need to bootstrap, right? If it was small sample sizes, things are not necessarily symmetric. The sampling distribution of X bar could still be skewed. So if you simulate the T distribution, you can get skewness, and that might work out better for giving intervals that actually cover as much as you think, with balance, right? That if it's misses 2.5% of the time below and 2.5% above, it kind of has your conceptual idea that it's kind of balanced. If it misses 5% above and 0% below, this kind of seems a little funny, right? So something, but a little more details will be forthcoming about what to focus on, because we'll kind of reduce in a little bit. Chapter 7 did confidence intervals. In hypothesis tests, we also had type 1 and 2 errors. So kind of that interpretation is, why are these different? You state hypotheses. Which is a false positive, which is a false negative, are the equal consequences. This concept of power, right? Not to do a specific calculation, but you do want a small type 2 error, you do want a good chance of rejecting the null if the null is false. So something about the concept, maybe that's a graph of it, a statement that you want large sample sizes, make things more accurate, therefore you get a better chance of showing that things are really different. We've done some things with maximum likelihood estimation, was kind of a big concept. So we've had a few things where we defined a maximum likelihood estimation. Right? So it would be possibly one of the ones that we've done before, going through that procedure and then asking a question. How do you compare this? How do you compare estimators?
So like bias.
Bias, variance, mean squared error is a trade-off. Yeah, that type of. So if you did it repeatedly or through a simulation. So maybe there'd be a little simulation output that shows a couple of estimators and how they compare. But this kind of procedure for going, taking the derivative of the log likelihood and something that equal to 0. Kind of going through the mechanics of that just because it's kind of an important thing. Right? There's more that could be done. The thing that we'll kind of go back through a couple of these things and was in a chapter is, what is a sampling distribution? We have a statistic, and what do we mean? So what is the sampling distribution? Why do we focus on that for estimating confidence intervals and things like that? So that was kind of a fundamental concept. It cut through confidence intervals, through hypothesis tests, through thinking about accuracy of estimators, and so describing that to somebody and how it's used. And I think that'll be enough material for a final, right? Not as heavy maybe on, and it won't be all of it, so I'll try to make this a little more specific since I think about it a little more, so you don't necessarily every formula. But knowing a few of them well can illustrate the general ideas. Okay, so have a good break. See you in the last week of classes. Yeah, thank you.
Thank you.
All right.
Thank you.
Sorry.
Yeah,
It was on like your August.
yeah, sweet, sounds good, yeah.
So you found something to work on together for the project?
Yes,
Good.
we're doing the, like, murder data set.
Yeah, right, it's pretty
Which
big,
gave
so.
us, yeah, it gave us like 19 pages, like, worth of,
Yeah.
like, once we, like, put all the tables on, so, yeah, we're gonna do that together.
Okay.
Thank you, have a good break.
You too.
Thank you.